Okay, in this video I'm going to go through the 2024 Level 3 Organic Chemistry paper. That is Achievement Standard 91391, Demonstrate an Understanding of the Properties of Organic Products. Okay, so here's the start of the paper. This is question 1. And in question 1A, it says here 2-chlorobutane exists as enantiomers or optical isomers. They've drawn a diagram for this molecule, and they've asked us to draw the enantiomers of 2-chlorobutane in the box below. Now, what we're going to do, when there will be an enantiomer question in every paper every year, there has been for the last 10 years, and what you need to do when you draw that is draw a three-dimensional representation of that. And then once you've drawn that representation, you then put a mirror image or a line in to represent the mirror and draw a reflection of it. Now, when you draw the three-dimensional image of it, you want a carbon in the center. You want one line going up to your top group or atom, your substituent. You want one line coming off as just a straight line to one that's at about 109 degrees. And then you have one that you draw as a triangle, as shown, a dark shaded in triangle, and one as a dashed line that goes behind. Now, you can possibly get away with not doing this as well as this, but this is going to be a very important skill that you need to practice. So this is the answer to this anyway. We have this carbon in the middle that has 4 different groups off it, and that's what gives it the property of being an enantiomer. And actually, for part 2, they want to explain why 2-chlorobutane can exist as an enantiomer. And it's because this carbon here in the center is a chiral carbon. And a chiral carbon is a carbon that is bonded to 4 different substituents, 4 different groups or atoms. And we just need to write that down here. Now, if we've done this properly, what's going to happen, how the grade they're going to give us for this is they're going to give us an achieved if we recognize that there's a tetrahedral arrangement and the groups are asymmetric about the carbon atom and identifies asymmetric carbon in the atom. So what they mean here is that there is a chiral carbon. So you can accept a chiral carbon is actually the better word to use here. If you can draw the 2 structures and explain the requirement for enantiomers, that is that you have 4 different groups coming off and there is a chiral carbon, then they'll give you a merit mark here. So you get an achieved and a merit. Right, so part A question, question A, part 3 from question 1. Here it says divide a reaction scheme to convert 2-chlorobutane into butanamide. They've drawn a diagram here of butanamide here, just in case we forget what it might look like. What we can notice on the butanamide is it has a carbon double bond oxygen here, and it might be, if we look at the products, we might start to realize here that we need to have a functional group on the end, and that functional group must have a double bond O, which is most likely going to be a carboxylic acid. So, however, in each step we need to give the reagents and the structural formula of the product. Now here is our initial reagent. Okay, this is what we're given, 2-chlorobutane. You can see that the chlorine is on the second carbon. We need it to be on the first carbon. So in order to do that, to get a functional group on the first carbon, and remember how I said that I was wanting to make a carboxylic acid, I'm most probably going to want to put an OH on here, but I need to undergo an elimination reaction and then an addition reaction. Now, if I want to remove a halogen from here, okay, what I'm going to need to add here is some hydroxide that is dissolved in an alcoholic solution. Now, that can either be potassium hydroxide, sodium hydroxide, or you might just write hydroxide OH minus. But in this case, I'm going to eliminate this and I need to make a double bond on the right here. So I'm going to use potassium hydroxide, an alcoholic solution. Now I'm just writing down that this is the minor product here. I'm not sure whether they need us to say this in the marking schedule, but I do recognize that when I take the chlorine away, I have to take an adjacent hydrogen away, and the majority of the time, using the Zaitchev's rule, we would take it away from the carbon with the least carbons, but we are taking away from the carbon with the most, so this is going to be a minor product. Now we're going to carry out an addition reaction, and I want to turn this into make an alcohol group on the right hand side. And so what I'm going to add here is I'm going to add some water in acidic conditions, or dilute acid. Okay, so I've got water / H plus. Again, using Markovnikov's rule, this is going to be the minor product. I'm just going to write that down. It might not be information that they need to know, but you know, I'm showing them that I'm aware that when I carried out this reaction, there were two different products, but it's the minor one we need to actually go ahead and make this butanamide. Okay, so I've got to this point and made an alcohol. If I want to make this carbonyl group here on the end, well, the easiest way here is to turn this into a carboxylic acid, and to do that, I'm going to carry out an oxidation reaction. Sorry, the other reagent, sometimes you can write the reagent up here as water / H plus, or just H2SO4 aqueous. Okay, so let's do this reaction. We're going to oxidize it to a carboxylic acid. So here I'm going to use acidified, so dichromate. So I'm drawing the iron dichromate here, but I'm / H plus means it's been acidified. I could have used permanganate acidified as well, but in this case I chose dichromate. Okay, so this is now our alcohol. Sorry, not alcohol, our carboxylic acid. Now we want to turn it into an amide, but I can't go straight to an amide to a carboxylic acid. If I add an amine to this here, they'll just undergo an acid-base reaction. The amine will grab the proton from the carboxylic acid and become an amide ion, and the carboxylic acid will just lose its proton. So what I actually need to do is to make an intermediate between the carboxylic acid and the amide. So I'm going to turn this into an acyl chloride. So you can see that here. And to do this, I need to add a reagent, and there's quite a few different reagents I can choose. In this case, I chose PCl5. You could choose PCl3. You could choose SOCl2. All of those are valid reagents to write down. I've just chosen one of them. Okay, so then we're going to go from here to the amide, and if we want to turn an acyl chloride into an amide, we just need to add some ammonia to it, concentrated, or ammonia dissolved in alcoholic solution, so NH3 alcohol, or I could write it concentrated NH3. So these are all the steps that I've gone through. In this case, they don't need us to say what type of reactions they are. In another test or exam, they might do that. So in this question, this is question 1A still, but in this part of the question, they gave you got an achieve grade if you did one conversion with reagent correctly, or you recognize that you had to move the functional group position to another place. Well, that's kind of generous of them. If you got 3 correct conversions with this, then you got a merit. So that would be 3 steps out of the 5. If you did it all correct, you got an excellence. And, you know, well done you if you did that. Okay, question B from question 1. Polylactic acid, PLA, is a polyester with various uses, including medical implants, tissue engineering, and 3D printing. It is made from lactic acid shown below. Okay, so if lactic acid is going to make a polymer, a polyester polymer, that means that this must be a monomer, and it's going to make ester bonds. Okay, so or ester connections, and we can see that from here. We're going to have to, it says in the box below, draw a section of PLA, 3 repeating units. Now we can see here that there are 2 functional groups. There is a carboxylic acid functional group, and there is an alcohol functional group, and that we know that we can react a carboxylic acid and an alcohol together with concentrated sulfuric acid as our catalyst to produce polyester bonds, or sorry, ester bonds. In this case, we're going to produce polyester. So I'm going to take this. And what the concentrated sulfuric acid does is it removes an OH from from here, an OH, and a hydrogen from here, or is it the other way around? But we remove a water completely, an H from one side, an OH from the other, and we join it together where we broke it. So we're going to end up with this molecule here. Now this molecule is a repeating unit. Okay, so the repeating unit here is our polymer. We've got 3 units, 1, 2, 3. Now, identify and explain the type of reaction occurring. Well, this is a condensation reaction because we are making we're making a long chain of polymers plus small molecules coming off that they used to see as condensing on the inside of a container, so it's called a condensation. And in this case, it's a condensation polymerization reaction. The OH and the alcohol and the carboxylic acid groups undergo a condensation reaction where water molecule is removed and an ester bond is formed. Okay, that's important. Because there's an alcohol on one end and a carboxylic acid, they can form long chains because we've got these 2 different groups that can react with each other. Now, how did they mark this? Well, in this question here, if you drew the polymer with the ester linkages and identified it as a condensation reaction, they gave you an achieved. If you could correctly draw the 3 units correctly and explained the condensation polymerization, they gave you a merit. Okay, so part C of question 1. Below is the structural formula of a dipeptide. So here it is. A dipeptide, remember, is a 2 amino acids that have been joined together by an amide bond. Now, here is the amide bond here. We can see this. Now, a peptide bond is just another name for an amide bond. So we've got this carbon double bond, O joined to a nitrogen, that's then joined to the other part of the molecule. So the first thing they wanted us to do here is circle the amide linkage in the dipeptide above. So I've done that. So the next bit here, it says, is the dipeptide can undergo a chemical reaction to form the following products. Here we can see, here are the 2 amino acids that it was constructed from. Now, once it has been broken apart, you can see that the NH2 on the left-hand side here has been turned into an NH3 or H3N+, and the same on the other molecule. Now, that happens because the dipeptide, so this peptide here has undergone hydrolysis reaction, okay, acidic conditions. That's what's, so we know it's undergone a hydrolysis reaction because we've broken the amide bond here, or the peptide bond. We know that it was under acidic conditions because the NH2 group that would be in the amine part of the molecule has been protonated. That is, a proton's been added to it, which means it must have occurred in acidic conditions. We also know because the carboxylic acid group hasn't lost its proton, that it can't have been hydrolyzed in basic conditions, or it's not in basic conditions, otherwise it would be a COO-. So the next thing they want us to do is draw the structural formula organic products formed when the dipeptide is heated under reflux with sodium hydroxide. So this is in basic conditions. So we're going to have the same molecule, but now it's in basic conditions. So the NH3 here on the left-hand side is going to donate its proton, and so is the carboxylic acid. So once the NH3+ donates a proton, it becomes neutral and it becomes NH2+. And once the COOH here, COO, has donated its proton, it becomes O-. Now you might, if you said it was specifically sodium hydroxide, you might just put the ion next to this, the sodium ion, but you don't need to. You can just leave this as a carboxylate ion like this. So you've got the amine on one side, carboxylic ion on the other. Now the other molecule is just this second molecule here, showing it has been protonated. So we're going to lose a proton from the amide group here. We're going to lose a proton from the carboxylic acid here and the carboxylic acid at the bottom, and so our molecule is going to end up looking like this. Okay, so hydrolysis. How has this question been marked last year, 2024? Well, what happened is if you identified the amide group and said it was a hydrolysis reaction, you didn't have to say it was under acid conditions, you said it was just hydrolysis and identified it's an amide or peptide, then you got an achieved. If you were able to draw a correct product, draw one organic product of base hydrolysis. So if you drew one of these correct, they let you have an achieved as well, and actually let you away with not taking the proton off the carboxylic acid, though, so you could have either, right? But I wouldn't let you away with it. I don't think. You should know that, and remember, when it's in basic conditions, the carboxylic acid loses its proton. Okay, and if you wanted a merit, you need to explain the process of acidic hydrolysis and give one correct structural formula for the organic product of basic hydrolysis. And if you wanted an excellence, everything has to be correct, right? So you have to explain here and get both products correct with having the correct charges on the carboxylic acids. Okay, so this was the last question of question 1, and the way that they marked this question in this organic chemistry paper is you got an E8 if you got 2 E's, you got an E7 if you got 1 E, which means, hey, if you got part C here all completely right, you get your E7. That's kind of nice. If you want an M6, you need 4 M's, M5 3 M's, and then 4, 3, 2, and 1. A's gives you an A4, an A3, an N2, and an N1. Okay, let's have a look at the next question. All right, question 2. Complete the table below to show the structural formula of the IUPAC systematic name for each compound. Now remember, don't be scared about the IUPAC, what it means. It just means what is the way that you've been taught to name things in your chemistry class. That's what the IUPAC system is. So the first one we have here is methyl propanoate. So hopefully you recognize that that is an ester. The methyl is the alcohol group, and the propanoate is the side that contains the double bond oxygen. Okay, so the carbonyl group. So, and remember, those two things are joined by an oxygen in the middle. So here we are, we've got methyl here and propanoate on the left. Okay, the second one, let's have a look at that. We can see that it's 5 carbons long, so we know that it's pentane, and we can see that it has a carbonyl group coming off a carbon, but no other associated groups with it. So this is going to be a ketone, because if it was on the end, it would be an aldehyde. Because it's in the middle, it's a ketone. It's coming off the 3rd carbon, so it's going to be propanone, propan 3-one. Sorry, propan, pentan 3-one, because there's 5. Golly, don't make that mistake in the exam. Now the next one here, what's the name of this? Okay, it's got 3 carbons in a row, and it does have this aldehyde group on the end, so it's going to be propanal. But it also has this chlorine group coming off the end carbon. Now you have to remember, because this is an aldehyde and it has a carbonyl group on the end, we always start numbering from there. So it's 1, 2, 3. The chlorine is coming off 3, so it's 3 propanal. It's 3 chloropropanal. And the last one here, we have butanoyl chloride. Now, if you remember, the oil chloride means it is an acyl chloride. That is a double bond oxygen with the chlorine coming off at the end. And it's got 2 hydroxy. Hydroxy is another way of referring to the alcohol group when we don't have the space at the end of the molecule to put it. So we can write it at the start of the molecule. It's coming off the 2nd carbon, and that's, we start numbering at the double bond oxygen. So here we can see the OH group is coming off the 2nd carbon, and here is our acyl chloride group on the end, 2-hydroxybutanol chloride. Now they want us to draw next to 3 constitutional isomers of C. So here is C. Constitutional isomers mean we have the same number and type of atoms, they're just arranged in different ways. So, well, let's draw the easiest one, that is a constitutional isomer. Let's just take this chlorine off here and put it coming off the 2nd carbon. There we go. That's our first constitutional isomer. Great work. The second one we could do is, well, you know what? We could take this double bond, instead of having it off the first carbon, we could put it off the second one. And here is another constitutional isomer. Exactly the same amount of atoms, just arranged in a different way. And the last one, well, I don't think there is another way that we can draw this. Oh, well, yes, we could, couldn't we? Couldn't we just draw this as an acyl chloride, propanol chloride? I could draw that, but actually I decided to draw this. It was an alkene. So this is my third constitutional isomer that has the same atoms, same number and type of atoms, just arranged differently. I could have drawn 3 carbons in a row, an oxygen here and a chlorine, but yeah, there's a few different answers you could have done, and I could have drawn the OH off another group. I could have drawn the chlorine here. So they just want you to draw 3 different constitutional isomers. So those are 3 of them, but they aren't the only ones. If you got 3 correct from part A and 2 correct from part A2, that's these ones, so 3 from here on the left and 2 on the right, you're achieved. If you got all correct in part A, they're going to give you a merit. Well, that's pretty nice. And sorry about that, I just clicked through. Yeah, so you have an achieved or a merit there. Okay, let's have a look at this next one here. So it says complete the flow chart. Well, that's kind of mean. They've already given us a reaction scheme to work out ourselves, and now we've got to put one in. Really important to practice up on your reaction schemes. It makes such a big difference to your grade. Okay, so here we're starting with propan-2-ol, okay, isopropanol, and down the bottom here we've got, what is this, an amide? Yep, so we've got an amide down here, which is N-propyl propanamide. Okay, now we need to fill in all the steps in this reaction scheme. Let's start with the one at the top. If we add concentrated sulfuric acid to this, we know that we're going to remove an OH and a hydrogen from the adjacent carbon. So here we are, we're going to produce propene. Nice. Now we can see here that on the left they're adding H2O in the presence of dilute acid, they could have written this, remember, concentrated H2SO4. So we're going to add an OH group and a hydrogen group to this. But if we look down here, this will go on further to make the same thing that comes when this breaks into 2. Then the actual OH group is going to have to be on the end, because it needs to be on the end to make this carbonyl group on the end. So we're going to produce an alcohol. It's going to be propan-1-ol. And essentially what they've done here, and this is a common way when you need to move your functional group from one place in your molecule to the other, is you carry out an elimination reaction and then an addition. So we've carried that out. Okay, so where's the next step we can break apart? Okay, so what's happening down here at the bottom? This is an amide. What would an amide break into? Okay, it's going to break into a carboxylic acid. Cool. If we carry out hydrolysis on it, it's going to break into a carboxylic acid. And I can work out that if I'm going to turn this alcohol into carboxylic acid, I'm going to oxidize it. So here I'm writing acidified dichromate as my reagent. Now, if I break this apart, and if I turn this into a carboxylic acid, it must have occurred in acidic conditions. So when this breaks apart, the amine won't be an amine anymore. It will be an amide. Okay, sorry, not an amide. It will be an NH3+. So we're going to draw this amine as an NH3+ here. Okay, and we're going to, the reagent that we use here, well, we must use, we've carried out hydrolysis, so it's going to be H2O in acidic conditions /H+. Now remember, this is kind of goes back to the question we did on the when we broke apart the dipeptide is that when we do it in acidic conditions, we produce the acid group and then the conjugate acid of the base group. This is this. Okay, so that makes sense when we look at this reagent here. We had an amine, but we added acid to it, which would have protonated this NH3, so that's the NH3+. Okay, that's cool. So now we just have to work out what is it that we need to do to get from an alkene to an amine. Well, of course, if we want to make an amine, we need a alkyl halide. So I could use a few different reagents, but I'm just going to go with trusty here, NH3 from this molecule here. I'm going to make it concentrated hydrochloric acid, right? So I'm going to make this into a chloroalkane, or what's this? 1-chloropropane. And that is our reaction scheme completed there. So how did they give us marks for this? Well, they're quite generous for the achieved. You get 5 of these and you get an achievement. Well, actually, that's not that generous. But if you get 7 of these things correct, they give you a merit. So that's kind of all the way down here. That's 2 not correct. And if you get them all correct, all the reagents and all of the intermediate products here, they give you an excellence. And if you did that, well done you. Very easy to make a mistake, so you need to really practice the reaction schemes until you're doing them without mistakes. Okay, next part to this question. The following table lists the structures for 6 different organic compounds. So we can see here we've got an alcohol, an aldehyde with an alkene on the other side. We have a acyl chloride with an alkene and an acyl chloride, and then we have a ketone here. Now, we've choose the appropriate organic compounds from above for the observations recorded from chemical tests. So we've got 2 chemical tests in each of these, each row of the table. So the first one is heating with acidified dichromate of one of these molecules causes a solution to go from orange to green. Okay, that's cool. That means that oxidation must have happened. Now that could either be an alcohol or it could be an aldehyde. So we either have 1, 2, or 3. But then they've said heating with Tollens reagent does not produce a silver mirror. Now remember, a silver mirror only occurs when we have an aldehyde, because the silver is only strong enough to oxidize the aldehyde. Sorry, to reduce the aldehyde. Oxidize. Let me see. Silver 2+ goes to silver. That's going from 1+ to 0. That's reduction. So it will oxidize it. Yeah, that's correct. So sorry. Does not produce a silver mirror, is not an aldehyde. So it's not 3. It's not 2. But it does react with acidified dichromate. It must be this alcohol. So this is number 1. The next one says heating with Fehling's reagent forms an orange-red solid. Okay, you might have been told this is Benedict's reagent if your chemistry teacher is a biologist. But Fehling's reagent is the name that chemists give to the same solution. It is just like Tollens reagent in that it will only oxidize aldehydes but not alcohols. So this one here is a really definitive test for an aldehyde, so it's going to be 3 or 2. But it says if we mix it with potassium permanganate solution, it causes the purple solution to decolorize to brown. Okay, so this is our test for unsaturation, or for a double bond. So we produce a diol from this and we add permanganate to it. So we must have here an aldehyde and a double bond carbon. So that must be number 3. The next one, mixing bromine water goes from orange to colorless. Okay, amazing. It's going to have a double bond. But also steamy fumes. Steamy fumes come when we add water to acyl chlorides. We're adding water because bromine water is just water with some bromine in it. Okay, so we must have an acyl chloride, which is either 4 or 5, but we also have a double bond, so it can only be 4. So those are our 3 answers. If you got them all correct and you did all of that work, well done. They give you an achieved for that. That's a bit stingy, Okay, so the next bit, they want you to justify the chosen structural formula for each of these three compounds. Okay, so we need to link it back to the observations. So one, why did we choose one? So in the paper, they don't tell you what the answers are, but you need to justify your answers. Now, of course, for one, the reason that we saw this is because the alcohol got oxidized to a carboxylic acid, right? This is an alcohol. So in compound 1, acidified dichromate changed color from orange to green because that primary alcohol was oxidized to the carboxylic acid. We can talk about the second part as well. Also, this would not be oxidized by a Tollens reagent, as Tollens reagent is not strong enough to oxidize an alcohol group. So that's the second thing we would use to justify that. Okay, for the number 3 that we chose for the second part of the table, we said that this is an aldehyde group. So, and there's an alkene group here as well. But this reacts with blue Fehling's reagent because it is an aldehyde, and the Fehling's reagent is strong enough to oxidize an aldehyde to a carboxylic acid. Okay, so this has been oxidized to a carboxylic acid. And the second thing here is it has a double bond. So when we add permanganate to this, then the permanganate will oxidize the double bond and produce a diol. Okay, so oxidized producing a diol. You have to remember from last year, if you haven't gone over again this year, that this will become a diol. And the last one here that we chose was 4. And 4, remember, we had this acyl chloride here, and that was, we knew we had that because we saw the steamy fumes. That's what an acyl chloride does. The water reacts with an OH from the water replaces the Cl, and HCl is actually produced at the same time. So those are the steamy fumes that we see. So we're producing a carboxylic acid. This is a substitution reaction. And the last reaction that we observed that were in our table was this one here, the double bond reacted with bromine water. Of course, this is an addition reaction. So the color change from orange to colorless is because it's an addition reaction. And it's going to add a bromine here, so it's a haloalkane as well as a carboxylic acid in the end. So in this case, they're going to give you, if you can identify 2 reaction types from here, they're going to give you an achieve. So if you said out of these 5 reactions that we observed, if you got 2 of them right, then they give you an achieve. If you can recognize at least 3 functional groups using compounds 1. So what are 3 functional groups here? Can you identify what they are? Then they give you achieve. If you can link 4 observations to the functional groups, okay, so you're saying it's the primary alcohol, therefore that's why it changed color, then they're going to give you merit of if you did 4 of them, right? If you can explain 3 reactions using compounds 1, 3, and 4. So any one of these 5, not including the second bullet point here, any one of the 5, if you can say, hey, this is the functional group, it underwent this type of reaction to produce this new functional group, there you go, you have got a merit. If you can justify 2 compounds in terms of observational functional groups and reaction types, and just a minor mistake in one of them. So if you made a minor mistake of this, then they'll give you an E. This is quite a lot of writing here, and it's quite of in depth, but if you got this, then well done. It's really important that you've done some of the practice with these types of observations and in class, because that really helps out with this. Okay, so this end of question 2. If you got 2 E's, they give you an E8, 1 E, and E7. Now you can notice from this writing here, an E is quite hard in this organic chemistry paper. 4 M's, M6, 3 M's, M5, and 4, 3, 2, 1 is A4, A3, N2, and N1. Let's have a look at the last question. Okay, so last question. Wow. Question 3. A student followed the procedure outlined below to prepare a sample of ethyl propionate. which we will remember is an ester. Maybe you carried this out in your an experiment in your classroom. Step 1, add propanoic acid, ethanol, and concentrated sulfuric acid to a round bottom flask. Step 2, heat the reaction under reflux for 30 minutes. Step 3, add sodium carbonate until the bubbling stops. 4, add water and separate the layers. 5, add a drying agent to the organic layer. And 6, distill the organic layer to purify the ethyl propanoate. Okay, describe the function of the H2SO4. Well, the H2SO4 is used to catalyze the reaction, make it happen quicker, but how does it do that? Well, it removes the water from the reaction. And because this is a it is a condensation reaction. Because this is a condensation reaction and we're producing an ester, that reaction is actually at equilibrium. And what the sulfuric acid does is, as it removes the water from the product side of the equilibrium, then the system, that reaction at dynamic equilibrium, shifts to the right and produces more of the products in order to replace the water, and in doing that makes more of the ester. So esterification reactions, we can talk about how that might work in relation to equilibrium. The next thing is give 2 reasons to explain why the reaction mixture was heated under reflux. Now remember, reflux is you have a round bottom flask, and sitting on top of that flask is a Liebig condenser. So it's the long piece of glass tubing that you sit into your flask, and which has cold water going around it, and that just does one thing: it condenses the gas that's trying to escape from your mixture. So any of the reactants on products that have evaporated or boiled, vaporized, are then, as they go up the condenser, cooled back down and are condensed back into the liquids and fall back into the mixture and keep reacting until they're turned into product. So heating under reflux allows 2 reasons. The other reason is we want to heat the mixture to make it happen more quickly. Okay, so we speed up the rate of the reaction by heating it up. Really simple. But because we heat it up, it means that we're going to have more of our reactants and products vaporizing, so we need to have something on the top to collect them, to push them back into the mixture. So we need to identify both points. We heat it up to make the reaction happen more efficiently, more quickly, and we put the condenser on to make sure that we don't lose any of the reactants and products from them vaporizing. We condense them back into the mixture, and that will produce a greater yield. Now, how did they mark this question? If you describe one function of concentrated H2SO4, you got an achieved. If you recognize one reason why the reaction was heated up, that is to make it happen more quickly, or because the condenser will catch any evaporated gases and turn them back into liquid to go back in the mixture, then that's an achieved. If you can explain 2 reasons why it is heated under reflux, that's a merit. And there isn't an excellence for this, but this merit part here is used with the next question to give you the excellence, next part of the question. Okay, so let's have a look at that. Why was sodium carbonate added? So if you remember the 6 steps here, we added sulfuric acid, we heated it for 30 minutes under reflux, then we added sodium carbonate. Well, you added sulfuric acid to it, okay? You added a carboxylic acid to it. At this time, usually added sodium carbonate dissolved in water, it's about 30%. When you add the sodium carbonate, it's going to react with any acid that's still there and neutralize it, right? So basically, we're going to neutralize the acid, any remaining propanoic acid or H2SO4. Explain how the distillation was used to purify the ethanol propanoate from the organic layer. So they said that step 6 was to distill. Now, if you remember the distillation setup, we have a round bottom flask, and then we have like a corner that has our Liebig condenser now on a sort of ramp shape, right? So it's almost horizontal, but not. It's pointing downwards, and so any liquid that is collected and condensed in it is that any gas that goes through our condenser will be turned back to a liquid and then will flow down the condenser and out into a collection container. Now, we have been told here that there are 3 different boiling points. We've got propanoic acid 141, ethanol 78.3, and ethanol propanoate 99.1. Now, one thing we should note here, what we did here is we added water to the separate layers in step 4. So when we added the water, then water will, one of the reasons that you add the water is it can dissolve all or any soluble things that's in the mixture. It will dissolve it, and one of the soluble things is ethanol. So ethanol dissolves in the water. So if we've actually added water and we've shaken into our separating funnel, and if we've put that in there and shaken it and then let the water off the bottom, and if we've done that a couple of times, we should have got rid of all of the ethanol. So we're really concerned here with propanoic acid and ethyl propanoate, and what we need to do is heat it up about 99 or 100 degrees Celsius, and if we do that, at that point the ethyl propanoate will boil, right, and all the gas will come off, but the propanoic acid won't, because its boiling point is all the way up at 141. So the ethyl propanoate will be separated from propanoic acid. Ethyl propanoate will go out of the flask, around the corner, down the condenser, and then we can collect it once it's been condensed back to a liquid. So the ethanol dissolved in the water. If we were heating up, we would have got the ethanol. If it hadn't been dissolved in the water, hopefully we would have boiled it off first before we got to 99. The reaction mixture is heated to approximately 99 degrees Celsius to purify the ethyl propanoate. Any unreacted propanoic acid will stay in the mixture as long as we don't get it up close to its actual boiling temperature, right? Its boiling point. So the ethyl propanoate vapor will rise, enter the condenser where it's cooled down and condensed to form the pure liquid ethyl propanoate. Now, this is quite challenging in this paper in that they gave us all these steps, but they didn't give us a picture of the equipment. So you kind of have to see a picture of it in your mind. Okay, so the answers. If you can identify that sodium carbonate neutralizes the acid, achieved. If you can say that the mixture needs to be distilled, because the compounds have we use distillation because the compounds have 2 different boiling points. That's another achieved. If you can explain how distillation purifies ethyl propanoate, if you can explain the evaporation and condensation process, then that's a merit. And if you can justify how it was used, so if we have all of these points and explained how we used the distillation and the different boiling points to separate the ethyl propanoate from the propanoic acid, then that will be an excellence point if you got the merit point from the previous question as well. Okay, so you need to take both of those together to get your merit. Okay, last question. Oh, is it the last question? No, two more sub questions. Okay, next one anyway. Consider compounds A, B, and C shown here. Choose one that has the following properties. Cannot exist as enantiomers. Now remember, we did enantiomers earlier in the paper. It's a carbon that has 4 different groups coming off it. So, well, let's do that first. So if we have a look at compound A, we can see that in compound A, okay, let me just... compound A here, we can see that this carbon has 3 different groups off it, can't be an enantiomer. This one has 2 hydrogens, so it doesn't have 4 different groups, and this carbon doesn't have 4 different groups. Compound A could be the molecule that we have because it said it cannot be an enantiomer. If we go to compound B, we can see the carbon on the left has 3 hydrogens. The next carbon has, it's bonded to a methyl group. On the other side, it's bonded to a CH2, NH2, which is a different group because it's larger than the methyl group, bonded to an OH and bonded to a hydrogen. This is an actual chiral carbon in compound B. In compound C, wow, the first one has 3 hydrogens of it, not a carbon chiral carbon. The second carbon, it looks like it could be a chiral carbon, but if we look carefully, it's got a CH3 group and a CH3 group. So it's actually bonded only to 3 different groups because these 2 groups are the same. So compound B cannot be our answer. Forms a silver mirror. It must be an aldehyde. So the only one that doesn't have an enantiomer and is an aldehyde is compound C, because compound A, remember, was oh no, that's, remember, compound A and compound C are the ones that don't have enantiomers, but they're also aldehydes. So it's still, sorry, compound B, you're still out of here. The second part didn't help narrow it down for us. But the last one turns damp litmus red. Blue, sorry, blue. So if it's turning red litmus blue, it must be a base. Which one of these has a base on it? This one here does. It has an NH2, an amine group, which is slightly basic and will produce blue litmus. Red litmus will turn it blue. So compound C is our answer. There we go, compound C. Explain our choice. Okay, so we just go ahead and say, well, compound C does not have any asymmetric carbon atoms. Actually, I would say chiral carbon atoms. This, I got this back from the marking schedule. They like to say asymmetric. Asymmetric, not sure is the best word, because like the carbon on the right here is asymmetric, right? It's not a chiral carbon. So try not to use the word asymmetric, use the word chiral. So it can't have enantiomers, that's cool. Compound C has an amine group, so it is basic. It will turn red litmus blue, and also it has an aldehyde group. So it is going to react with Tollens reagent and produce a silver mirror. So in this case here, if you chose compound C, you get an achieved. If you explained 2 of the points, it's a merit. Let's go on to the next question. Structural formula for the constitutional structural isomers of C5H9OCl that has the following properties. Okay, so they just want us to draw the molecule that has those atoms in it and has the following properties. Exist as enantiomers, optical isomers, must have a chiral carbon. Branched carbon chain, okay, so it's not just 5 carbons in a row, it must be at least 4 and 1 coming off, or 3 and 2 coming off. Produces steamy fumes, okay, I like that. Steamy fumes, it tells us initially it's going to be an acyl chloride. The acyl chloride must have 4 or less carbons in a row, because it has to have 1 carbon coming off, and it must be an isomer. Sorry, it must have an enantiomer, a carbon coming off. So here's the one that I've drawn. So I have 1, 2, 3, 4 carbons in a row. It has an acyl chloride group coming off, and it has a CH3 coming off the second carbon. I couldn't put the CH3 off the third carbon, because then this carbon would not be chiral anymore, because it would have 2 identical CH3 groups. This is the only place it can be to make a chiral carbon. So this is our only answer. The next one. Okay, so we have a different structural formula, C4H7OBr. Exist as cis-trans geometric isomers. Okay, must have a double bond. And straight chain arrangement, 4 carbons in a row. Causes a color change from green to orange to green when heated with acidified dichromate. It produces an organic product that does not react with Benedict's solution. To produce an organic product that doesn't. Okay, well, that's fine. So orange to green with acidified potassium dichromate, obviously it's going to be an alcohol. To produce an organic product that does not react with Benedict's solution. Oh, okay, so what that means is that it can't be, if you had an alcohol on the end, then you could potentially oxidize alcohol to an aldehyde and stopped, and then that product could go on and react with Benedict's solution or Fehling's solution. So it doesn't have an alcohol group on the end, but it does have an alcohol group, so it must be off the second carbon. It must have a double bond, and the double bond has to be in such a place that it has that the carbon, each carbon that's part of the double bond has 2 different groups coming off it. So this is the molecule that I've drawn here. So we don't have, we've got the OH coming off the second carbon, and we've got the double bond here on the end. It can be The reason I put the bromine on the end here is because if I'd put a hydrogen here, then it would not be a cis-trans isomers. So if I put the bromine here with the hydrogen, then we can have cis-trans isomers. And the OH coming off the second one, it will react with acidified dichromate and it will produce a ketone, but it won't produce an aldehyde. So this is our answer. This is our product. This is the final question here. If we can draw a branch chain molecule here, and or we put an acyl chloride group, and we drew a carbon double bond carbon, then that's, and this one down here, okay, and drew a double bond carbon here where it achieved. If we draw one of these completely correct, we get a merit, and if we draw both correct, we get an excellence. So if you drew a component of each, achieved. If you draw one correctly, merit, or both correctly, that's excellence. Which is good, because if we remember when they're marking this paper, oh, not for this question though. So in this question, you need 2 E's to get an E8 and 2 E's with a minor error to get an E7. You need M6, 4 M's, M5, 3 M's, and 4, 3, 2, 1 A's for A4, A3, N1, N2. And that's the end of this paper. If you take the grades you get from each of the questions out of 8 and you add them up, then you can then check to see where you got in the end, the mark for the paper. So if you got less than 7 or less, you're not achieved. 8 to 13 achieved, and 14 to 18, it's a merit. 19 to 24 is an excellence. One thing to note about the organic chemistry paper is there is a lot of problem solving, especially in this paper. So if you have revised well, you understand your reaction schemes, you understand your molecules and the properties of the molecules, you're in a good position, because there's just a lot of like sitting down and solving problems. Anyway, good luck with this, and have a look for the other videos I've done on the structure and bonding questions, and look for another video I'll do on this one.